Hello, everyone. In this video, I'm going to go over problem 4.68 from chapter 4. This concerns finding intervals of increasing and decreasing, concavity, as well as inflection points. So I'm going to go ahead and use Desmos and graph the function in question. All right, so we can get a basic idea of the function as it's graphed, and it appears that the function is increasing throughout all real numbers, and it appears to have potential concavity point right here, inflection point I meant to say. There appears to be also another inflection point here, because there's a concavity change from concave down to concave up. But in order to be sure, I mean, we can't be sure that it's here, in fact, because this is just, Desmos is marking the fact that it's crossing the y-axis. So we don't want to say that. And instead, what we want to use is the derivative. So we're going to graph the derivative, and we can see that the function is pretty much positive throughout, and it appears that the function is actually increasing for all real numbers. But indeed, if you look at the answer, you can see that that is not the case. So this, in fact, misleading. So to double check that, in fact, nothing is, mysterious is going on, we're going to use the Wolfram cloud system. So I'm going to define the function first of all. Of course, we use capital E to represent the Euler constant. All right, so then I'm going to ask for its first derivative, set it equal to 0, and then I'm going to ask Wolfram to solve for me this equation for x. And we can see that we have indeed a couple of solutions here. Two of them are complex in nature, but two of them are real. You have 2.97, 296, and 3.02721. So it appears that the derivative is equal to 0 at these points. So this is when, in fact, the curve, the first derivative changes signs, right? It crosses the x-axis twice. So those are these values here. So if we zoom in, we can in fact see what those are. There they are. So in fact, it's referring to these two values. So clearly, what's going on is that the function is decreasing between these 2 points. Otherwise, it is increasing. Okay, and hence you have these solutions, as you can see. The function is decreasing on this interval and increasing on the other two intervals, to the left of this point and to the right of that point. Okay. So, this illustrates that Desmos by itself may be misleading, and we still want to go ahead and use calculus to actually to find the points of intervals of increasing and decreasing. So the next question is, what are some intervals of concavity? And so it's best to graph the second derivative. This is a little more clear. So we have the second derivative is positive between these 2 points, and then negative between these 2 points. So that tells you that we have a case of concave up between these 2 points. And then to the right of that point, as you can see, that's the solution, that's the answer to that question, concavity. And then for concave down, we basically have from to the left of this point, as you have negative infinity to negative 0.517, and then between these 2 points, because that's when the curve is below the x-axis. All right, and then finally, what are points of inflection? So it looks like the second derivative changes signs from negative to positive. So this must be a point of inflection. This must be another one, and this must be another one. Now, these are actually points on the second derivative function, right? So they're not actually on the actual curve. So we must actually find the precise points on the actual curve, on the original curve, where the inflection points take place. Before we do though, I'm just going to double check that in fact these are the only inflection points by using Desmos. So I'm just going to use the same command. I'm going to ask for solve for the second derivative and set that equal to 0 and solve for x. And indeed, we have these three values, the same values in question. All right, so coming back here, what I want to do now is basically just plug in these points, right? So the first one is negative 0.517. I'm just going to say, all right, give me the point negative 0.517, comma, and then I'm going to plug in negative 0.517 into the function, and I'm going to ask it to just show me that point, and there it is. So while doing that, I'm going to turn off the first derivative, keeping the second derivative because I'm still using these points. Next one is 1.251. So I'm going to do 1.251, comma, f of 1.251. So I'm actually putting these points on the actual graph, right? And then the last one is just 3. All right, now we can turn off the second derivative. And here we have the actual full points on the original function. And those are the solutions that you see here. Okay, using the Wolfram Cloud, we could also ask Wolfram Cloud to plug in these values into the original function. So the way you do that is you just say, okay, I want f of x, and then I want you to take these outputs. The way they're labeled, by the way, is they're actually individual assignments. It says, let x be this value, let x be these values. So all we have to do is just say, plug them through f of x. And then it'll in fact do that. If you see the values here, 0583, 086, that's the y component, right? That's the y value when this x value is plugged into the original function f. So that's how it does it. Of course, you don't have to use this techniques. You could have just said f of negative 0.516903, and then it'll process that as well. But this is a fast way to just ask Wolfram to plug in all of these x values into the original function by using the evaluate or assign operator. It's / dot, and then you just call the output, the third output, that's what this %3 does. And since these are already put in a format where you make the assignment, you could just have f process those. So those are ways in which we can use both Desmos and Wolfram Cloud to solve this problem. I hope you found that helpful.